Good afternoon and welcome to this presentation on provenance and workflows in AiiDA. Since I won't have my webcam on for this presentation, a small introduction about myself. My name is Sebastiaan Huber. I'm a postdoc at EPFL and among other things, I'm a developer of AiiDA Core and AiiDA Quantum Espresso. And in this talk, I will talk a bit about how and when AiiDA stores provenance. I'll give a short introduction on writing workflows. And finally, I will give an overview of AiiDA's provenance model in its entirety. So let's start with the motivation. One of the core pillars of AiiDA is automated provenance, because we think keeping data provenance is important. But if we look at even a simple provenance graph of a workflow, where this is the computed property of a single material, and you see all the data provenance that comes before it, imagine having to manually store everything and link everything up. This would be, even for this simple case, already a humongous task. Never mind if you want to run this in high throughput and run many of these. So we need a task that automates this for us. And that's exactly what AiiDA promises. In the name, you will see that it's an automated infrastructure. It's automated not just with respect to running your workflows, but automated in the sense that it will automatically store the provenance of anything that you run. So when we talk about data provenance, just a quick reminder, what do we mean? When storing the data provenance, we just mean that whenever there's a data transformation, we store that in some kind of a database, the record of that data being transformed. So for example, if you have a calculation, here represented in this square, by the square, it has some input data that it takes and it produces some output data. By storing the data provenance means essentially storing a reference of that calculation in the database together with the inputs it took with these links, as well as the outputs that are produced. In this case, if these output data nodes are themselves reused for another calculation, they will be full history will be stored. So the question now is, how does actually AiiDA store this provenance automatically? So to explain this, it's easiest to do this at the hand of an example. So imagine we have the following simple arithmetic problem. We want to add two numbers and multiply the sum by a third. I have a very simple implementation here in Python. So we define two functions. First called add, that takes two numbers and returns the sum. The second one is called multiply, that also takes two numbers but returns the product. Now first we can call add on the two numbers, and its result we pass into multiply, giving us our final result. This all works fine to get us our result, but this result will not be stored anywhere, nor where it came from, so that it really was constructed through these input data, these input integers. So how does AiiDA enable you to store that provenance? You can do this through what's called a calc function decorator, that you can import from AiiDA engine module. And all you have to do, a decorator in Python is nothing more than literally decorating a function by putting it on the top, preceded with an @ sign. So you put add calc function, and the same for multiply. This is all that's necessary and required to turn these functions into AiiDA provenance functions. The only thing that we have to change now is when calling it, that the input nodes, or the input data if you will, these integers have to be passed as storable data types. And to do this, since they're integers, we wrap them into this int class, this int data type, that you can import from AiiDA or rem. So now when we call this, AiiDA will automatically store all the steps and records this in its database in the provenance graph. And the way it's presented is exactly like this. So these int nodes have now been represented by these green circles. So x and y are data 1 and data 2. And they've been passed into the add function, which is now represented as this calculation node in the database. It produced the sum, called d4, which in turn, together with d3, is passed into the multiply, which is also represented, and finally produces the final result, d5. What we have generated here is a directed acyclic graph. It's a graph because there's nodes and there's links connecting these nodes, and it's a directed graph because the inputs go in and the outputs go out. On top of that, it's acyclic because the causality principle tells us that it's impossible for an output to also have been an input at its own creation. So this directed acyclic graph has lots of interesting properties and allows you, as it becomes bigger, allows you to explore it through AiiDA's tools like querying. This will be presented in a later talk. So this shows you hopefully how easy it is to, when you have Python code, to turn it into an AiiDA provenance enabled code simply by adorning or decorating it with this calc function decorator and passing storable types. But not all code is well suited as Python code. Often you want to actually run an external executable on your local machine or maybe on some kind of a remote cluster. So how do we accomplish this? How do we run external codes through AiiDA such that AiiDA still keeps the provenance? To do this, you need what's called a calculation plugin. And how to implement such a plugin is not actually the focus of this talk, so I will not go into details. You will actually see this in a later stage of this tutorial. But imagine that we already have an executable that sums two numbers. It's some kind of a bash script that sums two numbers. And we already have created such a plugin that allows to do this, and we have called it arithmetic add calculation. And to call this through AiiDA, you just define the inputs in the Python dictionary. So we have our x and y, 1 and 2. Again, note that they're wrapped in this int data type. And in addition, now we have to define a code input, which references exactly this binary. So it tells you on which machine it is, in this case, the local host machine, and where to find the binary, so the absolute path. This is defined by this input. And then simply to run this code through AiiDA, which is called as run, which you can import from the AiiDA engine module, passing the class name, which is the plugin, and passing the inputs. So the implementation is different as it requires a plugin, but running is very similar as the functions themselves. So when you do this, this is what the provenance will look like in the database. So we see here a recording of the three inputs that we passed. The calculation itself, of course, gets a node in the database to represent that it was run. And instead of one, it now has two outputs. So you will always have, for these calculation jobs, you will always have a retrieve node, which is essentially a folder that contains all the output files that have been generated by the calculation. And optionally, but very often this is the case, these files are parsed, and the parser can create up as many nodes as they want. In this case, we have parsed the actual result, which is the sum, and stored as a separate node. There's quite a lot of advantages. I mean, in addition to the fact that it allows you to run external codes and not just Python code, these calculation jobs can also be run on remote machines through job schedulers. And AiiDA comes with built-in support for most of the well-known schedulers like Torx, Slurm, PBS, SGE, LSF, etc. And an additional nice thing about this is that the implementation is independent of the job scheduler. That is to say, you write the plugin once, independent of the job scheduler, and you can run it once, defining, let's say, passing the code on to run it on the local host. And now if you want to run the exact same calculation with the exact same inputs, but on a different machine that has maybe a different scheduler, all you do is change this code input, and AiiDA takes care of all the details dealing with the scheduler and even the fact that it's on a remote machine for you. Finally, unlike the calc functions, which you can only run one at a time, these calc jobs can be submitted to the daemon, which means that you can run many of them in parallel. This, of course, is very useful if you want to do high throughput computing. So let's go into the next step and go towards workflows. So far, we have seen how we can run calculations through AiiDA and tell it to store the provenance. And here was the example of the addition and the multiplication and the provenance graph that was generated. And the individual sequence of the calculations was recorded, but not really the how or why. This graph doesn't tell us whether we ran the addition at some point in time and then waited a long time. I mean, completely disconnected, simply reuse the sum for the multiplication, but they're not really connected. So the provenance graph doesn't really capture the logical sequence of it, if you will. And this is what we can use workflows for, not just to automate this, not have to manually launch the multiply after the add, but also to in the provenance of a recording of the logical sequence. To do this, you can use work functions. They work very closely similar to calc functions, as in they're also a decorator. And so we can use those work functions to create a simple workflow. So here I define a function called add and multiply that now takes three numbers. And the goal is that we sum the first two, and then the sum is multiplied with z to get the final result. And see how we reuse the calc function that we've written before. And so the work function just calls these calc functions. So first it calls the add function, passing in x and y to get the sum, and then calls multiply with sum and z to get the product, and finally returns the product. Now if we call this like this, this is the provenance graph that will be generated. So we see x, y, and z are passed into the add and multiply work function. It will call the add calc function with d1 and d2, which produces d4. And then the work function will call c2, passing in d4 and d3, which produces the final result. The added bonus of this is that in this trivial example, it might not as be clear, but once these workflows become very more complex and lots of calls and lots of levels, lots of layers, you can decide to just look at the logical provenance to hide the complexity. For example, here we just look at the links that are dotted, so that are part of the logical provenance, and you just see a much simpler picture. D1, D2, and D3 were inputs of this work function and produce this final result. We don't care about the result, about the underlying details. However, sometimes the data provenance is very important and you want to see it, but it's still there. And you can convince yourself that if we, in this left picture, ignore the dotted lines and the workflow nodes, so the logical provenance, you get back exactly the data provenance that we had before. But like calc functions have their limitations, work functions also have their limitations. For example, again, they can also be run at a time, and they cannot be stopped, if you will. And so we have designed a class called a Workchain that overcomes these limitations of the work function. It achieves the same goal as it captures the logical provenance of what you're doing, but it has a lot of additional features. As you can see here, a Workchain is a class, and it has the most important part of it is this define method, where you define the inputs. So we say here, this Workchain takes the inputs x, y, and z, and it produces the result, which is the sum followed by the product. And then there's this outline which explains the steps more or less that it's going to follow. So first it's going to do add, then does multiplication, and finally reports the results. You can see here how this is implemented. The add step does nothing more than just call again the calc function to do the work for it. And then the result is stored in this context, which is saved in between steps. So that allows us in the multiply step to access the sum, which is the intermediate result, and call the multiply calc function with the third input, z, that produces the product. And then finally, in the final step in the results, we just register that product as the output. So launching this will create the following provenance graph, and you can compare it to the provenance graph of the previous work function, and you see that it's exactly the same, except that the type of workflow is slightly different. In this case, it's a Workchain node, and here it's a work function node. But the rest of the provenance is exactly the same. However, the Workchain has lots of benefits over the work function. For example, unlike the work function that can only be run one at a time, a Workchain can be submitted to the daemon, which means that you can run many in parallel, which is of course typically what you want to do and allows high throughput computing. Moreover, the progress of Workchains is saved between steps with checkpoints. That's to say that if the Workchain crashes or your computer needs to be shut down or actually loses power, the next time you restart it, the daemon can continue from the last time it left off, and it saved its progress. With a work function, this is not possible. Either it finishes completely or nothing. For this simple example where the calculation is quick, this is not a big deal, but if you're running calculations through your workflow that might take hours or days, this feature becomes critical, because otherwise you wouldn't be able to shut down your machine. The process specification performed in the define method that we just showed also gives a nice overview and a lot of control over validation, and generates automatic documentation, which of course in the work functions you don't have. So the more complex your workflow becomes, the more powerful this define method and the process specification comes from the Workchain. Finally, it really captures the scientific knowledge and can be easily rerun. We haven't shown this here, but in the outline, the logic, you can really define complex logic with while loops, if conditions, and in a sense, it really captures the scientific knowledge of the scientist and allows these Workchains to be shared, and that can be run by by other people as well. And finally, these work chains can be reused as building blocks. There's additional functionality in AiiDA that we won't be able to show here, but that allow you to very easily reuse work chains in more complex workflows. AiiDA provides you the tools to store the provenance of the calculations that you run. However, there are ways of losing provenance still. And this is basically the result of the fact that workflows cannot create new data. Doing so anyway will cause the loss of provenance. To show you what I mean with this, it can be a bit vague, let's go back to this first example where we're adding two numbers and multiplying with a third. So again, we take the work function that we have, but remember in the first version, we let all the actual calculations be done by the calc functions. In this case, let's see what happens if we do the following. For the addition, we call the calc function, as we should, but then for the product, instead of calling the multiply work calc function, we do the multiplication ourselves directly in this work function. So we take the sum, multiply by z, turn it into an int node, and we store the product and return it. If we run this work function, this will be the provenance graph. We still see the representation of the work function, and it called this add calc function. But finally, it didn't call a multiply calc function, and it just did the multiplication itself. So even though the final result is stored, there's no record in the provenance graph that the result is basically based on D4, this intermediate sum. There's no direct connection between it. And this is what we mean when we say that workflows cannot create new data. It has the power to return, but the actual who created it will be lost. To explain why this is the case, we have to look a little bit more at what the properties of workflows. And it has to do with the fact that they can return. So work functions and work chains, being workflows, can return the outputs that have been generated by the calculations that they call. But that also means that so essentially they can return nodes that already exist. But it also means they can return nodes that are part of their inputs. So take it, for example, this work function called maximum that given 3 integers will take the largest one. So we sort the array, the list of these integers, and take the last one. The provenance graph that will be generated looks like this. We see here the work function maximum with the 3 inputs, and it returns one of its own inputs. And now you see there is a cycle. And so this breaks the acyclicity of the provenance graph, and so no longer a DAG. At this point, this is a choice that we made as developers for AiiDA, and we wanted to keep the DAG for the data provenance. So we decided to split the data and the logical provenance in two. What this means is that if you only look at the calculations and data, which is the data provenance part, it's guaranteed to be a DAG, but as soon as you include parts of the logical provenance, so you include the workflow nodes and the return links, this is no longer guaranteed. So this is why we have two clearly distinct types of processes in AiiDA. The calculations that can create new data, and the workflows that can call other processes, where processes is the combination of both calculations and workflows, and they can return existing data. And that's to say they can return the data that has been created by the processes that they have called. So there's a very important distinction. It can be a bit unintuitive in the beginning, but you'll hopefully this makes this a little bit clearer. So now that we have discussed all components, the calculations, the data, and the workflows in AiiDA, this is an overview of the terminology in AiiDA's provenance design. So these nodes, the magenta ones are calculation nodes, either a calc job if you run them through a plugin, the external code, or a calc function if it's a simple decorated function. The same for the workflow variants, they're orange, and then the data nodes are always green, and you see the various links that are possible. I mean, this is just an example graph that can be generated, but there's lots of possibilities, of course. Then there's the ORM hierarchy. This is useful if you later during the tutorial, if you have to perform queries and have to work with specific link types, if you want to traverse your provenance graph. And these are the ORM classes that you can use to identify certain nodes that you might be interested in. So at the top level, we have our node. Every entry in the provenance graph is a node, which is split in two types. It's either a process node, so a workflow, or it was a data. The data comes in various subtypes like a code, structured data, dict, and these can be extended through plugins in AiiDA. Process nodes, in turn, are split into either workflows or calculations. And as we've already seen, each of these have been split in two based on which type of process they have been run. So work function generates a work function node, a calc function generates a calc function node, etc. Finally, there's six types of links, as defined here by the hierarchy. You have a data that goes into a calculation node as an input calc link, data for workflow node as an input work. Calculation creates data, and a workflow node returns data. And finally, a workflow can call either a calculation or it can call another workflow, creating sub-workflows. Finally, there's an important concept. There's a distinction between processes and node. When you run a process, so either a workchain or a calc job, the engine will run a process and it will store a node in the database as a proxy, as a reference of itself. And so there's this duality between processes and nodes. And so here you have a small table that gives you an overview of which process class gives which node class. So calc job, this is this arithmetic add calculation example that I showed you, will create a calc job node. And this is for calculations that are performed by external codes. And likely a workchain produces workchain node, which are workflows with these multiple steps that are shown. Finally, each process has a state that's useful to see what its current state are. There's two types, an active state and a terminated state. The active state can be created, running, or waiting. And if it's terminated, it's either killed, so it's killed by the user. It's accepted, some exception occurred during execution, or it's finished. Everything ran nominally. And finally, this, you don't have to look these now, but these are some useful properties on the nodes that you can use to inquire its state. For example, the process state, the access status, and some properties, whether it's finished okay, or failed. Finally, some words about how to launch these processes. We've already seen a few examples in the snippets that I've shown you. But in principle, any process can be launched through these 4 launchers, where the terms running mean that the execution will block the interpreter. So you will have to wait for that process fully to continue before you regain back control. Whereas submitting a process means that you will submit it to the daemon, so you get control back immediately as the daemon runs in the background and will take care of it. So if we start with run, this method, you can import it from AiiDA engine. And the syntax is you call run passing the name of the process, so this could be the calc job plugin or the workchain or even the work or calc function, and you pass the inputs as keyword arguments. And this will return you the dictionary of the results. There's some variation. Run get node and run get bk do exactly as run, so it will run blockingly, have the same interface, except that in addition to the result, they will also return a reference of the node and the pk respectively. This is useful if then afterwards you want to request some information of the node itself, like its final status, whether it was successful or not. And finally, there's some shortcuts. Instead of having to import all these variants, you can just import run, and you can access the get node and get bk as attributes on this function. So you can do run.getNode instead of run_getNode. But this is just a small shortcut that can be useful. Finally, there's the submit. So that's really completely different, where submit, it will not start to run it in the interpreter, but will submit it to the daemon. And so as a result, what you get back is not the result, but the node. It's basically a future. At that point, it won't be done yet. Finally, there's another way. If you get a lot of inputs, maybe your line gets very long as the keyword arguments. So instead, what is useful, you can define the inputs as a dictionary, normal Python dictionary, and you can use parameter expansion, the ** inputs, to automatically expand this into keywords, which is useful, like I said, if you have very many inputs. Then, as a last step, I want to show you some of the Verdi commands that are useful when dealing with processes. We have Verdi process, and this is the help string. So you can see there's various commands: kill, list, pause, play, report, show, status, and watch. And I will go through some of the most important ones. The primary one is Verdi process list. This will, by default, list all the active processes. You can also use flag -a to show also the completed ones, the terminated ones. And so this will give you an overview of the processes that are currently running. So here you see that I have a bunch of work chains running. There's Verdi process status, which is especially useful for work chains, and it will give you an overview of the call stack. So you see here a relax work chain that called the PW base work chain that called in turn this calc function and the calc job with their statuses and so forth. Verdi process report is the same for work chains. It gives you a representation of all the logs that have been emitted by the work chain. And these are human readable messages. So you will get to see, okay, first it launched this base work chain that in turn launched this PWA calculation. You can see that it's indented. Then you can interact with the processes while they're still running. You can decide to pause a certain process should you want to. If a process is paused, you can resume it by calling Verdi process play. If it no longer should be run, you can kill it with Verdi process kill. And remember that if this is only possible for for active processes, if it's already terminated, it's already stopped, it will return this error that it's already terminated. So with this, I want to end this presentation. I want to thank, of course, all the developers of AiiDA Core and all the collaborators for all the plugins. And with that, I want to end this presentation. Thank you.